Going here. Let's do this. Got some YouTube Friday I'd like to get to. Jerson? Got Carter. All these slackers. Just in time, maybe. Here we go, last one. All three are gone today. You got some slackers here. Don't be one of these guys. All right, couple of items here. Someone was asking me. Was it you who asked me about the spring? Someone was asking me about it. You take the spring. Your homework problem where you have a mass and then the spring and you have to figure out how much it's squished to begin with. Who was that? Someone asked me after. I got it. Yeah, I figured it out. We were just thinking about it wrong. So this is what it is. So this is the question. And this is a great question because he got me. Okay, I didn't know the answer to this. Right? There was a problem. You had to figure out how much sag. Right? This guy was like this, and then it was sitting on a spring. Right? Right? And then the answer is, so you had to figure out what its like static equilibrium was. Right? How much does it deflect right there? And how we calculated that, right, is just by the definition of a spring, right? K times delta is equal to, in this case, the force, which is just mass times gravity. So that initial displacement was just mg over k, right? That's great. That's fine, right? But then, what was your name? Of course it was. Of course it was. Ethan over here was like, well, why can't I do the same thing and think of it in terms of energy, right? Can't I work it out where if like I think about this thing being lifted a certain height and then I let go of it and then it's just going to go down and all the energy that was in my mass times gravity ended up going into my spring. And I'm like, well, you should be able to do that, right? And I went through the whole thing and, Ethan showed me his derivation and I went through it. And when you do that, you get 2 mg over k. Right? That's what you get if you do it by the energy. It's like, why do we get 2 mg over k? It's like, fuck if I know, right? I'm sure we're missing something. Does anybody see what it is? When you do it via energy versus doing it this way. So this one's twice. This ends up being twice. This ends up twice what this is, right? So this is what you would call the static equilibrium. This would be if I gently put the thing on and just like kind of let it slow down and then held it there. Or it would be the one, that's what that mg over k would be. And so that would be just not moving at all. If I do it the other case, if I'm thinking of it in terms of energy, what this is the displacement. It would spring back at this point. I would let go of it. I would let go of it and it would squish a little bit and then it would go back up. And then it would come back down and then it would go back up and then it would oscillate around this 2 mg over k. So there'd be, does that make sense, right? There'd be energy stored in that spring and it would give it back and it would fight up against the gravity and then the gravity would win again and it would just go back and forth like that. And it would be oscillating. It'd be oscillating about your initial start point and 2 mg over k. What would really happen, right? What would really happen is there'd be damping in there and this thing would settle out at mg over k, right? It would oscillate about mg over k and then eventually it would just kind of settle down and it would hit your static equilibrium. Look at that. I came back at you. Yeah, I got it. It took me a while. Because I was like, God, your logic was sound, but then I'm just like, oh, wait a minute. It's gonna spring back, right? That's wrong. By the way, that's vibrations. When you guys take vibrations in the future, you're gonna be doing stuff like this, right? It is all about oscillations and at what frequency is it gonna oscillate back and forth and stuff like that. Oh, All right, so that's one item. Okay. YouTube Friday is going to be actually very topic oriented today, so we're going to finish our rigid body kinematics. Oh, no, we're going to finish particle kinetics. Okay. Oh, not this one, though. We want the one that's not filled out. Okay. So we did this. We did a ballistic pendulum. We said energy is not conserved across a collision, so be very careful of that. This is the very last topic before we go into rigid body stuff, and it's this idea of angular momentum. Okay? We've talked about linear momentum. We have not talked about angular momentum yet. Okay? So this is a pretty quick derivation. We're not going to spend too much time on it. I wrote down most of the derivation. But basically, an object that's traveling, in this case, just a particle. This particle is traveling, has a certain velocity, right? And it has linear momentum. That linear momentum is mv, right? Mass times velocity is that. But then you could also think of this thing as having angular momentum about a certain point. Right? So if I was saying, what's the angular momentum of this about the origin here? It would have a moment arm over here. That'd be r. Okay? And we'll define, so basically the moment, we'll go through the full derivation in a second, but this is kind of what we're gonna build up to. This term of angular momentum is r cross mv. Okay? It's just like, I'm going to write it down here in a second. It's just like a regular moment, right? A regular moment is r cross f, right? Angular momentum is r cross linear momentum, okay? And so we need to tie that to forces. Right now, that's just a definition, right? Angular momentum is just r cross mv, just like similar, right, to moments. Moments equal to r cross f. If you remember that from statics. My handwriting is particularly bad today. Oh gosh. R cross F. Right? It's very similar to that. Okay, but somehow I need to tie my moments to this angular momentum. Okay, and that's what we're just real quickly going to do. I don't think we have any homework problems on this. We need this concept later on when we go into rigid bodies, but right now, this is all we got. So we start out with this. To do this derivation, we've done this every time we've done a derivation. We start out with F equals ma. That's going to be a given that we have. Okay. We are then going to take and we're going to do r cross with both sides of that. R cross with the right and the left, and then you distribute that evenly, and then we get r cross ma. Uh-oh. Okay. Right, so I just did r cross and I distributed to both sides of that stuff. Okay, so there's my moment on the left-hand side. I'm going to try to write this on the right-hand side. This right here, I want to write slightly different. I want to write that in terms of angular momentum, and all this stuff to follow is all about that. Okay. So the first thing we do is just say, this is all just trying to come up with another way to write all r cross ma. So if I take the derivative of r cross mv, so I've kind of jumped ahead. If I do the derivative of r cross mv, I apply this, the product rule works for this as well. So I take the derivative of the first thing, leave the second thing alone, then I take the derivative of the second thing and leave the first thing alone. So that's what this is. It's just using the product rule. So there's the derivative of the first thing, left the second thing alone, first thing alone, took the derivative of the second thing. Okay? So we've done that. This right here, this is just velocity, right? That's velocity. Velocity crossed with velocity, that's going to go to 0. So this whole term goes to 0. V cross V is 0. Okay? And then dv dt right here, dv dt is my acceleration. Okay? How the velocity changes with respect to time is just acceleration. And so the whole point of doing all that was just to give you this, which says that the derivative of r cross mv is r cross ma. Gosh dang it, I hate when they do that. They freaking change it. Uh-oh. Nope, that one. It's r cross ma. Right? So then so now what I'm going to do is I'm just going to take this derivative of r cross mv and I'm going to put it right here where this r cross ma is. I could substitute in what r cross ma is, and that's what I get right here. This next little step is r cross f, right? So my moments equal the derivative of r cross mv, and r cross mv is my angular momentum, right? So this is just HO. I don't want to quit doing that, Debbie. Oh man, they got me. They changed these around. I'm an old man. I can't figure it out. Right, this part is just HO. Right, so that's what the next little step is I just substituted in that. So moments are equal to dHO dt. So it's how the angular momentum changes. I'm just going to take this dt now and I'm going to put it on this side, right? And then I can integrate, and then that's where we finally got it. We're where we wanted to be. This is our grand conclusion right here. So moments acting over time, right? That's what this is. Moments acting over time is equal to the change in angular momentum. Is all that we're showing here, which is very analogous to what we did for linear momentum, right? Forces acting over time cause a change in linear momentum. Moments acting over time cause a change in angular momentum. That's all we're doing there, okay? Let me just write that out. Acting over time cause a, forces acting over time cause a change in linear momentum, and moments acting over time cause a change in angular momentum. I'm sure that's very analogous to what we did for moments. Or sorry, what we did for forces. It kind of just flows from that. You would think that. So if you had, like I said, I don't think we have any homework problems that we deal with this. You might have one, but you're just looking at that. So what also comes from this, what we did last time when we were talking about linear momentum, is once we derived this, we said moments acting over time cause a change in angle. We said forces acting over time cause a change in linear momentum. We then said, well, what if there isn't any forces acting over time? What happens to angular momentum? And that's where we derived linear momentum. That's where we derived the conservation of linear momentum. We're going to do the same thing here. We could do it here where we talk about conservation of angular momentum. That'll be conserved too. Just like linear momentum is conserved, angular momentum can be conserved. Okay. So again, if you have a case where your moment's 0, right? Or the other case would be that the other case would be if the resultant, right, something like this, if the resultant moment would be 0 over a certain amount of time. One of those two. Then what happens is up here in this equation, right? Up here in this equation, if this E is equal to 0, then HO2 is equal to HO1, right? HO2 is equal to HO1. Right? If there's no moments, then the angular momentum before has to be the angular momentum afterwards, right? And so R2 cross MV2 is equal to R1 cross MV1. Okay, so then I have this little example here, okay? What I'm doing, I'll show you a video of this shortly. You probably see, I'm certain you've seen this before in physics, but you know, I'm sitting in here, I got two big masses in my hands, right? And I'm sitting on a frictionless stool and I'm spinning around in a circle, okay? In this particular situation, there's no moments that are acting on anything. Sure, like my hands are holding up the masses, but then the masses are pushing down, right? And that's kind of out of plane. If I just look at this thing from up above and I'm looking down on myself, right? If this is a frictionless stool, it's not really frictionless, but it's close. But if it's a frictionless stool, there's no moments there. So then the conservation of angular momentum should work out, right? So if my hands are out wide, I have a certain angular momentum. Right? Ends up just being the crosses kind of go away, but R1 MV1 is equal to R2 MV2, right? And so what I do in this situation is I start spinning with my arms out and then I pull my arms in. If my arms go in, then what has to happen? There's a speed up. Right? I have to speed up because this has to stay there. That angular momentum is conserved in this. Angular momentum is conserved in this, right? So this has to always be the same constant value, right? And so if my radius, if my r goes down, then my velocity has to go up, right? And vice versa. If my r goes up, then my velocity has to go down, has to slow down, okay? Let me find this video really quick. I gotta dig in some folders here to find it. I don't want to accidentally show you like an exam or something, right? you would hate that if I did that, right? Slow with them spread out. Tuck them in. Lift up. All right. Spread back out. That would work. Slow with them spread out. Okay. So we got a couple versions of it. This is Yasmin, my TA from a couple years ago. I put her to work doing this. Going slow with them spread out. Tuck them in. And it speeds up. And then spread back out. Slow down. Tuck them in. Hey, look how cool it is. It works. It's real. Perfect. Oh, there's me pitting out a little bit. I'm a sweater, so I think I'm a little bit better than she is. Like a figure skater. I did. Oh, that's a later demo. So I used to bring this to class, and I did injure a student once doing that. Because I was like, get up here, and then as I put the masses in his hands, and then I spun him, and I was like, now tuck him in, and he like tucked him in, and he went like flying off to the side. So it was. I've decided to do pre-recorded videos in that regard, and I'm too lazy to carry the stool over here. Because it'll give away that I'm not one of you guys. If you're carrying a stool across campus with like some masses and stuff, they're like, that guy's not a student. I don't want to give it away. Okay, so if you heard me say this is how figure skaters get going really fast, right? So when the figure skater comes around the corner, right, and they usually even start with their leg out. They come around the corner, they got their leg out, and so they have all their mass really spread out, right? And then once they kind of launch themselves and get going, they have a conservation to make it. There's no other moments acting on them, right? There's very little friction on that ice. There's very little, and so if they can concentrate their mass, right, and then bring themselves and have as smallest like radius as possible, then their velocities should go up. According to this YouTube, I'm sure it's true. This is a world record. I don't think it is, but according to YouTube, it is.
Download the free Booking.com app today.
Okay. So then this is a couple years ago. I went on this journey. I was like, oh my gosh, look at that. Let's look at some other things. So this is pretty cool. A student shared this with me. So this is a wheel that they get spinning really fast. So they have a water jet, and then they have a skateboard wheel, right? And they're just like, what if we get this thing going really fast? What'll happen? And it's pretty neat. Oh. Also, don't do this at home. Sorry, that was a slow-mo thing.
And today we're going to be doing something a little more pink. Shoes, the pink high miles per hour. Okay, so let's strap it up and...
Oh. So what happened there? By the way, it flew off and then like embedded in the ceiling. And so, as I'm saying, don't do it. They're lucky they didn't get hurt because they didn't think it was going to do this. So what happened, right, is this has nothing to do with conservation of angular momentum, by the way. They just got it going really, really fast, right? And then there's some centripetal acceleration, right? The outsides of that wheel have to be accelerating back towards the middle, right? And if they're not accelerating back towards the middle, then they fly off on a tangent, right? What provides that acceleration back towards the middle. There's got to be a force there, right? In all of our problems we did in class, there was a string, right? There's a string that was holding it back. In this case, there's no string. And so what it is, you'll learn about this in mechanics materials, the hoop stresses. The hoop stresses, it wants to spread out, but then the wheel goes into tension to try to hold itself together. And like I said, you haven't gotten to that yet, right? Okay, yeah, you'll get to it. You'll do pressure vessels, and there's things called hoop stresses. But it's just the tension capacity of the wheel will keep it doing that. But it's a very elastic material, so it gets going super, super fast, and it starts failing the material in tension, and that's why it like spreads way out, and then eventually it fails. Because it can't accelerate back towards the middle anymore because you've exceeded the capacity of the material. I did a similar experiment, but I had an air like a air compressor, and they have the little concentration thing, and I had it on a fidget spinner, and I was like, zzz, it was in front of my kids, and then it was doing that, and I was like, it was going super fast. I was like, I probably shouldn't do this so close to my kid's face. Okay, so that's a thing. So then I saw that fail. Okay, so then we'll go to this. Now, when I saw that happen, when I saw a video with that. When I saw that, it reminded me of this movie. This movie, I think it's called Mission to Mars. It came out around the same time as The Martian. Martian, really good. Mission to Mars, not good. Have you seen the Mission to Mars? So this happened in Mission to Mars. Trigger warning. I'm going to tell you the trigger warning. This is gross. So if you're don't. Okay. This is the end scene. Yeah. It's coming up here. This is very similar to the skateboarding trail. Okay, all right. And I apologize. I told you it was gross. We're okay then because I gave you more. The centripetal acceleration got so much that it overpowered his tension capacity of his body. Okay. Oh no, there's one more. Actually, that's a really cool one. That was just funny. Then there's this. So this is. Which one is the good one here? I think this is the one I want. Okay. I'll tell you what's happening in this in a second. Okay, so what's going to happen is they put a camera on this rocket, the Maypheus 5, right, that they're launching this out. They're launching something into space, some sort of payload into space, right? So if you think about like a rocket taking off, right? This is stuff I didn't really thought of. Going up in the air, right? What happens if it gets like the wind hits the top here a little bit, or something happens where it gets off a little bit, right? So like with like the space shuttle and stuff like this, they go up and they got their boosters adjust, right? So it's like, it's like, oh, it's going this way, so it goes psh, 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 psh. Does that make sense, right? It's adjusting. The bottom part is pivoting so that they keep going straight up, right? If they didn't do that, then, and say it was off a little bit, it would go and then come down and crash, right? So there's some sort of adjustment that's happening, right? Now that could be pretty expensive. Like when you have people on board, that's right, you obviously want to make that happen. And so if you don't have people on board, you just have payload and you want to send it up, what they actually do is they throw a spiral. which is pretty interesting, right? That's why, because that spiral, so they make the thing twist around. So if it's off a little bit, well, we're gonna have some angular momentum that's going like this that are gonna keep us going straight up in the air. And so they literally throw a spiral, right? They make this thing start spinning quite a bit. But then when they get up into space, they can't have the thing still spinning, right? Because you don't want to have your satellite constantly spinning around, so they have to get it to stop. And so they use this thing called a yo-yo D-spin, which involves this conservation of angular momentum. Okay, we'll see what. I think they literally just strapped a camera to the outside of it here. See it coming out here in a second. Mach 6.5. Somewhere. And do a little adjustment. As you said. Okay, so what it did, right, is it had these little masses that were like attached to it right here, right? And then it got going, and there's like spin, and then when they do the yo-yo D-spin, and they release those masses, and so it's like putting your arms out, look at that thing. So it's like go fast, boom. And they stop because that R got, in that case, was the opposite that we were doing. The R got really big, so then the omega or the velocity had to go down in order to get it to stop. I thought that was pretty cool that that's what they actually do. And then what happens though, right? You could imagine that so once you release those things, they're just attached to springs or to strings rather, and then they go out like that, and it slows down. Well, if they left the strings on, then they would start wrapping around the other direction and then catch it and start going the other way. But what they do is they have like explosive bolts that then release them off into space. There's a lot of. I did a little research. Some people don't like this yo-yo D-spin because all these rockets that get sent up. These ones get sent up a lot, right? You only hear like space launches are big, but like these little payload ones get shot up a lot. And there's all these little yo-yo D-spin masses just floating around in space at this point. But these aren't. This one's not in orbit either, though, right? This one just went straight up. I'm gonna watch it play again so you can see. You wouldn't be doing this to astronauts on board. That'd be quite a ride. You can see that string going around. So mechanicals do kind of cool stuff. It's kind of neat to see it from that perspective. Oh yeah, just want to pause to see. Notice the curvature. Notice the curvature. It's flat. There is curvature. That's a real picture. That's the part, though, honestly, with flat earthers that as a flat earther, this is the hardest thing to wrap my head around, is how every video ever that you ever see of space, there's always curvature. It's always round. Like how the massive conspiracy it would be in order for every video you see from space, there's curvature every time, forever, right? Like how would that ever be possible, right? That everybody always agrees, yeah, right at the end, let's curve the video. Every frame of this video, we're gonna curve it and just to fool them to think that they live on a round Earth. Okay, and then it eventually goes back down. I think that's it for yo-yo D. Oh no, we got look at this one. Another failure associated with rotating. So brakes failed on this thing. See the blades itself failed under tension, probably, right? Because of that centripetal acceleration as it went around, and they failed, and then they took out its own base and went down. All right, you guys ready for some hard stuff now? Let's do it. Let's start this process. From here on out, nothing's review. I don't think you did rigid body stuff in high school or in your physics. All right. So some common things here. Right, rigid body motion. Right, we're gonna do rigid body motion planar. We're gonna start out with some 3D and we're gonna immediately get into planar motion. Right, and then at the very end, we'll go into 3D. But again, we're gonna take the same process. We're gonna do kinematics first. Then we're going to do kinetics. We're going to F equals ma. We're going to work energy and impulse momentum. Right. What's really nice is that even though we learned it for 1D stuff and that was easier, the same procedures. Same procedures you use for F equals ma. Same procedures you use for work energy and impulse momentum. Same procedures, just to get a little more complicated because now our bodies have distributed mass and they have and they're non-deformable. So let's get into this. What is rigid body motion? So first thing, like I said, is it's rigid, which means non-deformable. Right? In mechanics of materials right now, you have deformable bodies, right? You take your object and you pull on it and then it stretches, right? Or you have a beam that goes across and you push in the middle and it bends, right? That's deformable. Those are deforming and it's causing internal stresses and stuff like that. We're just going to pretend our objects are non-deformable. They don't move. They do though. I mean, they do squish and move and stuff like that, but that's another class when you have to do dynamics and deformable bodies, okay? Let's keep going with that. That's like a grad level course there. In mechanics of materials, you're learning about bodies and resultant stresses. I gotta fix my thing here. Here we pretend bodies do not deform. Okay. The other thing that happens in here that complicates things is we have mass is distributed. Right? We can no longer just go in and say, hey, we're going to concentrate my mass at a single point. We have to take into consideration that the mass is spread out, right? Which is going to complicate things. And then our motion now has translation. That's what we've been doing so far. What we've been doing. Right? That's what translation is, just an object moving from one place to another is translation. And rotation. Okay, that's the new part. Okay, So that's what we're doing. They're rigid, non-deformable. That makes it a little bit easier, but then mass is distributed. That makes it harder. And then motion has translation and rotation, makes it a little bit harder. Okay. We have some new components associated. We're gonna have a new material or a new object property that's gonna be floating around called a moment of inertia that we have to start dealing with. Different moment of inertia than what you're dealing with in mechanics materials. Okay. So then a lot of this has to do with it. So we're going to have rotation about a fixed axis. Usually these things involve, like I showed you, things rotating about things that are rotating, right? We got, something like this. This is what we're working towards. And so how do we kind of characterize this motion and solve these types of problems? Okay. So what we do is start out just in 3D and some key concepts here. And so this is a big blob that's kind of rotating about that axis, right? So some key things here is, what is the velocity of A going to be when this thing's rotating around? 0, okay? What shape will B trace out when it's rotating around? Circle. That's circle. That's exactly right. Right.
No.
Oh, you son of a gun. Well, I guess I'll just have to do it freehand. Got rid of my angled. All right, that's gonna be tracing out a circle, and then A isn't gonna be moving. Okay? What's some key concepts there? Each point on the axes has a velocity of 0. Okay? It's not moving, right? If the axis was moving, then it would be moving. But in this case, if it's a fixed axis, it's not moving. All other points trace out circles. Any point on body has same angular velocity. Right? There's actually translational velocity, and then there's angular velocity. Okay. A and B both have the same omega, is what I'm trying to say there, right? Even though they're on the same body, they have the same omega, but then their velocities of those points actually change. Like, how much are they actually moving? A's spinning, but it's not actually moving anywhere. So that's a concept that throws people off quite a bit, is they're like, well, this omega must be different than that omega, but they're both the same omega because they're both attached to the same body. The omega is associated with the body, not the point. Okay? You know what, I'm really mad at this. Used to let me draw ovals off shit. Motherfuckers. And they used to let me rotate them, but I can't rotate them anymore either. Okay. So then we're gonna drop the 3D now, right? That was 3D up above, and we're just going to planar motion. Just look at planar motion. And so again, this is the same object, but now we're looking down on it from above, and then that's what this is the world we're gonna live in for the next few weeks, is just the planar stuff. There's there's 2 other axes that things could be rotating around, but we're not gonna go into that, okay? All right, so then if we were looking down on this, B, B would be making a circle. Nope, that's not that size. Let me adjust it. It'd be have the center about right there. It'd have a center at A, and then B would be tracing out a circle. So you can see that circle a little bit better right there. This is the path of B. Right, and you can see that A won't be moving at all. Okay, so some key concepts here. This is a fixed axis of rotation about A. So that's what we're dealing with. A is a fixed point in the middle. Then we're going to define angular velocity. Velocity And vector notation, vectors are going to be super important from here on out. Angular velocity of vector notation. So this is going to be omega, same angular velocity we had in particles. That's omega. That's equal to d theta dt, how that angle's changing, right? We also sometimes call that theta dot. Okay? And then in vector notation, these are going to be omegas in the k direction. In vector notation, omega is going to be in the k direction. And actually, in planar, all of our omegas and alphas are in the k direction. But then keep in mind the whole right-hand rule that we talked about before. We rotate our fingers in the direction of omega. That's going to be a positive. It comes out of the board. And then if you rotate your fingers in the direction of omega, it's going to be negative going into the board. Okay? Where there's lots of right-hand rules that we're going to use throughout here, but that's what this is. And so that omega is it's the direction of the axes that it's rotating about. So, you know, if this thing was rotating with a positive omega, we rotate our fingers like that, and our thumb is coming out. If it was rotating with a negative omega, then you rotate your fingers, and then that direction is pointing into the board. Okay, we talk about angular momentum. Sorry, angular acceleration. Angular acceleration, again, is just going to be alpha. That's the time rate of change of omega, the omega dt. We call that omega dot. We can also call that theta double dot. And again, just like up above, this is going to be in vector notation, that's going to be alpha in the k direction. And it's really key to do that. We're going to have, like I said, vectors are going to be a big part of our life as we move forward. Okay. All right. So then we got to just setting up to how to solve these problems. Okay. So then one other thing here we got to say. This is just a review of circular kinematics from particles. And this is with normal tangent. Just a review. Right? When something was traveling around in a circle, right? Because we have circles. We just said that. Like B is going to be traveling in a circle about that fixed axis, right? And so if we have that here, okay, just to show you, since we have circles, let's just look what our kinematics is. If I want a velocity of something that's on a circle, right? I do r times omega, right? R times omega gives me the velocity of a point, right? That's it for particles. So if the radius gets bigger, has the same omega, then the velocity will get bigger. If I go down, it goes the opposite, okay? So that's how we're going to define velocity. And then accelerations are going to have two components, right? An r alpha and an r omega squared term. We'll come back to this one a little bit later. The key thing I want here is just this r times omega, right? Of my velocity. So I tried to build up to how do I figure out what the velocity of B is doing, right? In this thing, what's the velocity of B? Well, if A is 0, I can figure out what the velocity of B is, just take an r times omega. It'll tell me what that is, okay? Okay. But then what we got to build up to is what if A is moving as well, right? So if I want to say what is B, well, I got to figure out what the velocity of A is doing, and then I could take a step out to B using circular kinematics, and that's exactly what we do. And so that's we're going to use this relative motion to describe that. Okay. So now this body, right, isn't fixed. So this body it's a blob that's flying through space and rotating. Okay. So A isn't fixed and B isn't fixed, but I could still come up with a relationship. If I can figure out what the velocity of A is, I can then take a step to B. Right. Show you what it means in real world. Right. This point right here is not fixed. Right. This one is. Right. But this one is not. And so can I take a step from B over to C if B isn't fixed? Well, I got to do this relative velocity stuff, okay? Come back over here. So that we do, just generally speaking, in terms of vectors, we did this once before when we talked relative velocity. That's RA. I could take a step to RB. This would be RB is seen from A. B is seen from A. And I can get over to B by going through A like that. Right? And then this is RB. So just to kind of put that into words here, or into equations, RB is equal to RA plus RB is seen from A. Right? Just vector math is all that is. If I want to get to the position of B, I can go through A. RB is just equal to RA plus RB is seen from A. Okay? Same thing, if I want velocities, if that's true, then velocities will also be true. Velocity of B is equal to the velocity of A plus the velocity of B as seen from A. Okay? And what I just said, right, the velocity of B, oh, it's hard to read that A there, isn't it? Right, if I know the velocity A, I could step over to B. B is traveling in a circle about A. B is traveling in a circle about A, so I can use my circular kinematics there, and I could just say, yeah, well, VB is equal to VA plus RB is seen from A times omega, right? Because it's traveling in a circle. R times omega tells me that velocity in terms of omega, okay? That's just kind of generally speaking what it'll really look like in vector notation. In vector notation, it'll be this. Get used to that equation. We're going to be using that a lot. Okay? The velocity of B is equal to the velocity A plus omega crossed with RB is seen from A. So we got to do a little cross product, right? I don't think we've actually done a cross product yet in this class, so I'll show you the way that I do cross products in a little bit. There's ways to do that. There's easy ways to do that. There's hard ways to do that. I do it with the right-hand rule. You could do it with your calculator. Okay. Let's do. We got 4 minutes here. Let's kind of start this one. Okay. So what this one is, it's just an example of what we're going to do with these things. Let's just write down one of these things. So we're given omega A and alpha A. Right? So these are known. So this is a fixed point, and this is a fixed point, and this gear is rotating around, and it's touching this gear, and they're locked together at point P. Okay? And so if I make alpha, so if I make A spin around, then B is going to spin as well, right? Because they're attached to each other. And how do I kind of step around and figure out what alpha and omega are, right? First of all, right, are they going to be rotating the way that I have them drawn? No, right? They're not going to be that way because, right, if I spin this one this way, then that one's going to end up spinning back that direction. But with all of these problems, so say, always just draw them positive. And then what'll happen is at the end, it'll turn out to be negative, right? Your answer will turn out to be negative, which means that it's not going that way, it's going the other way, okay? That's easier. The other way you could do it, this gets really crazy, is I could say, okay, well, my intuition says that it's going this way, and so my answer can have it going that direction. So your answer will turn out to be positive. But then if your answer turned out to be negative, it means that it wasn't rotating this way, and the answer actually is positive. See, it gets really confusing. You can lose yourself. So just always draw them in as being positive, and they'll end up being negative. And then that just means they're negative. Simple as that. That way it's easier to deal with it. Okay. So that's one thing. So it's drawn that way. And so our answer should be that alpha and omega, B, will be negative numbers. They'll be negative of what alpha and omega A are. Okay? And so what we do, right, what we're going to do in this situation is we're going to take a step from A over to P. Okay? I'm taking an A over to P because it's on the same body. I can do that, right? And then I could take a step from P over to B, or I can go B over to P. But this idea of I'm going to start at one point and work my way over to another point, that's the process. You start out at a point that you know something about, and you take a step to one of the points that you want to know something about. Okay, so in this situation, I know what the velocity of A is. What's the velocity of A? 0, right? It's not moving. Then we take a step from velocity A over to the velocity of P. Let's just do that really quick, and then they'll let you go. So what we do, you go VP is equal to the velocity of A, something I know, a point that I know something about, plus omega A as a vector crossed with RP is seen from A. Write it down just like that. Every time. The easiest way to do these things, just start out with that. Velocity A is 0, okay? So then we write down what we know about this. Then we actually put in the vectors here. VP is equal to omega A is in the K direction. So I put it down in vector notation. And I'm going to cross that with RP is seen from A. RP is seen from A would be this vector right here. Okay? If I'm at A and I'm looking at P, and so in this situation, that is just going to be RA in the I direction. Everybody see that? It's just RA. Signs are super important. You got to be really careful of your signs as you go through here. Right? So I'm at A, I'm going to P. It's in the positive I direction. So now at this point, you do this cross product, right? In this case, right, you know, right? You know, your intuition says if this thing's rotating around like this, point P should be going vertical here in the J direction, right? Your intuition will tell you that. There's certain situations that it's not going to be that clean. It's not going to be really obvious which direction it's moving, or it's going to have multiple components and stuff. So then that's where this cross product comes in. Let the cross product do that work for you, okay? So we'll cover this more next time, but how you do the cross product is you take your hand, do your right hand rule. That's how I like to do it. And I have it go in the direction of the first thing. So K is going this direction, and I'm going to cross it with the second one, which is I, okay? And I get positive J. So omega in the K crossed with RA in the I will just be R omega in the J. I guess it's just omega A, RA in the J direction. Right? And then after I do that, like I said, you let the cross product do the heavy lifting. You let the cross product do the heavy lifting, but then make sure it passes the stink test, right? Like I went through this and I got that omega A, RA is in the J direction. And I look at my drawing and say, is that right? Yeah, that's right. Right? Could there be a case, like if I would have gotten this as being a negative, then I'd be like, well, wait a minute, that's not right. Or if I got it going in the K direction, that means you did your cross product wrong. Okay? So we'll take off from that next time. Because now I know the velocity of P, and I can step over to B, or I can go from B back to P and set them equal to each other. That's what we'll do next time. All right?